Okay, so when h is time independent, that's what it is. How about when h has a little time dependence? What do I call a little time dependence? A little time dependence is an idea designed to make it possible for you to solve the equation even though it has some time dependence. So you could have Hamiltonians that are time dependent but still have a simplifying virtue. So h of t is time dependent, but assume that h at t1 and h at t2 commute for all t1 and t2. So what could that be? For example, you know that the particle in a magnetic field, a spin in a magnetic field, is minus gamma b dot the spin. And you could have a time-dependent magnetic field, b of t times the spin. I'm not sure this is the constant gamma that I usually call gamma, but it may be. Now, then, if the magnetic field is time-dependent, but imagine its direction is not time-dependent. So if its direction is not time-dependent, then, for example, you would have here minus gamma bz of t times sz. And the Hamiltonian at different times commute because sz commutes with itself. And the fact that it's time-dependent doesn't make it doesn't make it fail to commute. So if you have a magnetic field that is fixed in one direction but changes in time, you can have a situation where your Hamiltonian is time-dependent, but still at different times it commutes. And you will discuss such case because it's interesting. But later on, as we do nuclear magnetic resonance, we will have the more interesting case in which the magnetic field rotates, and therefore it's not that simple. So what happens if you have a time-dependent Hamiltonian that actually commutes? Well, the claim is that u of t naught is given by a natural extension of what we had before. You would want to put the exponential of minus iht, but the reason this worked was because the derivative with respect to time brought down an ih over h bar. So one way to fix this is to put t naught, h of t prime dt prime. So this is an ansatz or try this. Look at this. If the Hamiltonian were to be time independent, you could take it out, and then you would get t minus t naught. That brings you back to this case. So this looks reasonable. So let me call this quantity r of t. And then you notice that r dot of t, the derivative of this quantity with respect to time, well, when you differentiate an integral, the upper argument, you get just the integrand evaluated at the time represented by the upper argument of the upper limit of integration. So this is h of t. And now, here comes a crucial point. You're trying to differentiate this u is really e to the r. And you're trying to differentiate to see if the equation holds du dt. So what is du dt? It would be d dt of 1 plus r plus r plus 1 3 factorial r. And now what happens? You differentiate here, and the first term is r dot. Here you would have 1/2 r dot r plus r dot. And then 1/3 factorial, but 3 factors, r dot r plus r dot r plus r dot. But here is the claim, r dot commutes with r. Claim r dot and r commute. Why is that? Well, r dot depends on h. And r is an integral of h's. Well, but the h's at different times commute anyway, so this must be true. There's no place where you can get a contribution, because dot is like an h, and here's an integral of h's. So since the Hamiltonians are assumed to commute, r dot commutes with r, and this becomes like a normal derivative of an exponential, in which you can move the r dot to the left everywhere, and you're differentiating the usual thing. So this is r dot and times the exponential of r. So actually, that means that we've got pretty much our answer, because r dot is minus I over h bar h of t, and e to the r is u. So we got du dt equal this, which is the same as this equation. So the only reason a derivative with respect to time would not give the usual thing is if r and r dot fail to commute. And they don't. So you can put the r dot here. You can put the r dot on the other side, because it commutes with r. But it's better here. And therefore, you've got this very nice solution. So the solution is not that bad. Now, finally, I want to discuss for a second the general case. General case. So that's case, there was a 1, a 2, a 3, h of t general. What can you do? Well, if h of t is general, there's not too much you can do. You can write something that will get you started doing things, but it's not obviously terribly useful. But it's interesting anyway that there's a way to write something that makes sense. So here it is, u of t and t naught. I'll write the answer and explain how it looks. And then you will see that it's okay, it's interesting, but it probably is not the most practical way you can solve this problem. So here it is. There's an acronym for this thing, T. It's called the time-ordered exponential. This operator does something to the exponential function. So it's a definition. So I have to say what this time-ordered exponential is. And it's the following. You take the exponential and just begin to expand. So 1 minus I over h bar, or I'll put like this, plus minus I over h bar, integral from t naught to t of dt1 h of t1. So far, so good. I've just expanded this. Now, if I would continue expanding, I would get something that doesn't provide the solution. You see, this thing is the solution when the Hamiltonian at different times commute. So it's unlikely to be the solution when they don't commute. In fact, it's not the solution. So what is the next term here? The next term is you think of the exponential as you would expand as usual. So you would have here plus 1/2 of this thing squared. So I will put something and then erase it, so maybe don't copy. 1/2 minus I over h bar squared. And you would say, well, t naught to t dt prime h of t prime, t naught to t dt double prime h of double prime. Well, that would be just an exponential. So what is a time-ordered exponential? You erase the 1/2. And then for notation, call this T1 and T1. And then the next integral, do it only up to time T1 and call this T2. So T1 will always be greater than T2 because T2 is integrated from T0 to T1. And as you integrate here over the various T1s, you just integrate up to that value. So you're doing less of the full integral than you should be doing, and that's why the factor of 1/2 has disappeared. This can be continued. I could write the next one would be minus I over h bar cubed integral t naught to t dt1 h of t1 integral t naught to t1 dt2 h of t2. And then the next integral goes up to t2. So t naught to t2 dt3 h of t3. Anyway, that's a time-ordered exponential. And I leave it to you to take the time derivative of that and at least to see that the first few terms are working exactly the way they should. That is, if you take a time derivative of this, you will get h times that thing. So since it's a power series, you will differentiate the first term and you will get the right thing, then the second term and you will start getting everything that you need. So it's a funny object. It's reassuring that something like this exists, but in general you would want to be able to do all these integrals and to sum them up. And in general it's not that easy. So it's of limited usefulness. It's a nice thing that you can write it and you can prove things about it and manipulate it. But when you have a practical problem, generally that's not the way you solve it. In fact, when we will discuss the rotating magnetic fields for magnetic resonance, we will not solve it in this way. We will try to figure out the solution in some other way. But in terms of completeness, it's kind of pretty, in that you go from the exponential to the time-ordered exponential, and I think you'll see more of this in 806.